Hello, Trigonometry. These are the video notes for trigonometric form of complex numbers. So complex numbers are a concept typically taught in your college algebra class. Anytime you were talking about I, rationalizing I, operations with I, those were your introduction to complex numbers. So a complex number can be any number, including numbers with I. So the standard form of a complex number is a plus bi. Now keep in mind, if the b is 0, then we're just talking about normal numbers like 2, square root of 5, negative 7. Those are also complex. Oops. So the first thing we want to introduce for trigonometry is how to graph a complex number and what the magnitude of a complex number is. Magnitude, denoted by the absolute value bar, a plus bi, is the square root of a squared plus b squared, which is also just the length of the hypotenuse when the complex number is graphed in standard form, which I'll show you. For a complex number in the form a plus bi, to graph, you graph the ordered pair a, comma b, where the x-axis is named the real axis and the y-axis is named the imaginary axis, which you can see on the grid I've provided in these notes. For example, we're going to graph each number and find its magnitude. So our first number is 2 plus 2i, which we're going to graph as the ordered pair 2, comma 2. And so that goes here. And that's how you graph that complex number. And so this is that vector from the origin. Now the hypotenuse, if you guys tell, the reason this is trig is because this forms a right triangle with the x-axis, and the legs are 2 and 2. According to the Pythagorean theorem, we should be able to do 2 squared plus 2 squared and get the length of the hypotenuse, which is why this is the formula for magnitude. So we've got 4 plus 4, which is the square root of 8, which means the magnitude of this first one is 2 radical 2. Then we have the example called 4i. So if you can tell, it's missing the a plus bi. So it has the I, coefficient of 4, but it doesn't have the a, which means we're going to graph this point as 0, comma 4. Now magnitude is just that length. So if we graph 0, comma 4 right here, we know that this is just a length of 4. But we can always set up our magnitude formula to include 0 squared plus 4 squared as justification for the magnitude being 4. For our next example, we're going to graph negative 3. So if you're considering your a plus bi form, this is considered a complex number, and we're going to graph it as negative 3, comma 0, since it doesn't have a complex part. That's here, and the magnitude of that is just 3. Magnitude must be positive. It's just your length. Does not include direction. Finally, the last example we want to graph is negative 1 plus 5i, which we're going to graph as negative 1, comma 5. The magnitude of that is negative 1 squared plus 5 squared, which is just the square root of 26. That one doesn't simplify. And it's graphed, pretend that line is straight, it's graphed right there. So this is how you graph and find the magnitude of a complex number. Next up, we want to convert our complex numbers into trigonometric form. So I'm going to copy down part of the answer from above. To convert a complex number in standard form, so z is our notation, we'll say z equals, or refer to our complex numbers as z. This is standard form, and this is trigonometric form, which is the goal. That means we need to know what r is. R is the magnitude, and what theta is. Theta is the angle formed by that vector when you draw it on your typical grid. So from the previous examples, this magnitude was 2 radical 2, this magnitude was 4, this magnitude was 3, and this magnitude was the square root of 26. I'm actually going to scroll back up to the graph to think about theta. So looking at this first example, and I realize it's quite small, let's redraw this right triangle. So for the first one, we had a right triangle. The x was 2, the y was 2, this was a right angle, and theta is formed with the origin. So the question is, how much is theta? Well, using trigonometry, which is the point, this is the opposite side, this is the adjacent side, and we can find theta as the inverse tangent of 2 over 2. And so this creates our formula for theta, which we're going to use every time. In the same way that r is always going to be the square root of a squared plus b squared, theta is always going to be the inverse tangent of a over b asterisk caveat. And I'll explain that with the next example, or with a different example. So here we have inverse tangent of 2 over 2, which if you type into your calculator, you should get 45 degrees. Now looking at where theta graphed, is 45 degrees a reasonable answer for this angle right here? Since the graph is in quadrant 1, 45 degrees makes sense. And that's what we're going to stick with. I sine 45. And that's how we convert standard form into trigonometric form. The next examples are a little bit easier, so B and C specifically. Let's take a look at B. B was graphed straight up and down vertically. Well, that angle is just 90 degrees. We know this. We've memorized our 4 major quadrants. Same thing over here. -3 is just 180. We know this. We've memorized our quadrants. So this one is just simply 4, and I'm going to use the shorthand version, CIS, 90. And this one is 3, CIS, 180. Just make sure that you don't mistakenly put a negative on this answer, because the 180 takes care of the fact that cosine is negative, since cosine of 180 is -1. Finally, we have our -1 plus 5i. So I'm going to regraph that one. That was in the second quadrant and was quite narrow. And if we use our theta is equal to the inverse tangent of 5 over -1, go ahead and plug that into your calculator. Just make sure that you're in degree mode. We get -78 degrees. And that is our first real problem, because there's no way that this angle in quadrant 2 is -78. Since tangent has a period of pi, to fix our answer, we just need to add 180 degrees. That's going to give us 1 tangent rotation away. That tells me that the angle is 101.3. Well, 101.3 is a much more reasonable angle measure for this angle right here located in quadrant 2, so I'm confident that 101.3 is the correct answer. I just wrote 103 instead of 101.3. 101.3. Okay, last thing we need to talk about. So what we just did above would actually be considered converting between forms, because we were taking a standard form expression and turning it into trigonometric form by finding the magnitude and the angle. Now we need to go the other way. We have the magnitude as 12 and we have the angle as 250. But this conversion is much, much easier. We can just type this into our calculator. So we're going to type into our calculator 12 cosine of 250. And that gives us -4.1. Then we're going to type into our calculator 12 sine of 250, not including the I. And that gives us negative, so I'm going to switch from a plus sign to a minus sign, 11.3, and just make sure you put the I. So when you do this, A is just your first term typed into a calculator, and B is just your second term typed into a calculator without the I coefficient. The I. Like so. Same thing over here, except I need you guys to be vigilant all the time and aware all the time, because 240 degrees is on your unit circle. And so if it's possible to leave your answer exact, I expect you to leave your answer exact. Let's get just a quick peek. Here's 270, here's 240, and in this quadrant everything is negative. So this answer is going to be negative, negative, like the one above. So cosine at 240 is -1/2. So we're going to do 12 times 1/2. So your calculator would actually get this one perfect. Minus sine at 240 is rad 3/2. So we're going to have 12 times rad 3/2. Keep in mind, I already put the negative, I just put it out front. So our final answer for this one, calculator is going to have no problem with the -6, but unless you have the Casio style, this one you're going to need to use your unit circle for, because it should be -6 rad 3. And then the I we typically write in front of the square root as opposed to behind, but as long as it's there, I'll accept it. So this concludes the video notes for lesson 19, an introduction to the trigonometric form of complex numbers. Thank you for watching.